In example 8, we're going to take a look at this function and sketch its curve out. So let's first note that there's not going to be any symmetry on this. Also, there's not a situation where this guy is not defined. Okay, so we don't have any asymptotes or holes or anything weird like that. Also, the end behavior of the function is going to grow without bound, okay, in both the positive directions, okay. The reason for that is because you take a third root, you square something, okay, it becomes larger, and then you multiply it by the square, that becomes larger, both in the positive direction. Okay, this will become positive, this will become positive, so we're heading up on both ends. Now, let's take a look at f prime. So let's go ahead and do the math up there. We're going to use the product rule here. So the derivative of the first times the second plus the derivative of the second times the first, just like that. And now what we can do is just try to simplify this a little bit. Okay, so what I'm going to do is I'm going to pull, I'm going to rewrite this like the following. We'll write it as 2/3 x, 2x times, or divided by 3 times x plus 1, that's this guy right here, to the 1/3. Now they're both, if I leave one x in and factor one out, and then if I also factor out a 4x, I'm going to end up with this. Let me walk you through it. I'll do the whole thing out here. So I've got a 1/3 in here on the bottom. So this is really 2 over 3x plus 1 to the 1/3 times x squared. So I can really write that guy on top like that. And then this will be plus. Now if I put a 1/3 down here on the bottom, an x plus 1 to the 1/3, that's multiplying top and bottom by this guy right here. It's not an issue. So this will be 2x times just x plus 1, like that. Okay, but now I'd like to be it over 3. So if I multiply the bottom by 3, I'm going to multiply the top by 3, so that'll give me 6. Just like that. Now what we're going to do is we're going to combine what we can here. So this is going to be 2x squared plus 6x squared plus 6x over 3 times x plus 1 to the 1/3. So this right here is going to give me 8x squared plus 6x over 3 times x plus 1 to the 1/3. And so I can factor out a 4, I can factor out, what can I factor out here? We can only factor out a 2x, and then we're left with 4x plus 3, like that. And this is 3 over x plus 1 to the 1/3. So this is the derivative. Okay. Now, so what? What are we going to use that for? Well, first things first. Let's go ahead and see if there's any issues where the derivative is not defined. Well, f prime of x is not defined when x is equal to -1. Because at -1 I get 0. The third root of 0 is 0 times 3 is 0. When x is equal to -1. So there's an issue there. Okay. Now let's take a look when f prime of x is equal to 0. That's when the numerator is equal to 0. So that occurs when x equals 0 and x equals -3 3/4. So if I drew a sketch of this guy out, I've got some important features. At 0, by the way, when I plug in 0 into the original function, I get 1 times 0, which is 0. So I know that 0, 0 is a point, and I also know it is a critical. It's a critical point. A min, a max, maybe some kind of inflection. Who knows what's going on there, okay? But it's a critical point nonetheless. Now I have another critical point at negative 3/4. And when I plug in negative 3/4 into here, I get out some mess, but I know that it's going to be positive. Okay, now how do I know that? Well, if I plug in negative 3/4 here, I can work through that math. So we've got negative 3/4 plus 1 to the 2/3 times negative 3/4 squared. So this would be 1/4, because that's going to be positive, the 2/3, okay, times 9/16, right? And so this is ugly here, okay? I got to square and then take the square root, okay? Or excuse me, take the cube root. So this is going to be a pretty small number, but I'm going to multiply it by this. It's still going to be positive. Okay, so I know at negative 3/4 I've got some positive value. This is a critical point. So I got those two guys there. I also know at negative 1, there's a situation. When I plug negative 1 into here, I get 0 times 1, so I still get 0 out. So there's a point here, okay, but the derivative's not defined here. So that's an indicator that I'm looking at a peak of some sort or some kind of cusp, because it is continuous here. I'm going to be able to come into it, but the derivative doesn't exist. Okay, so that's kind of the big picture that's going on here. Now, what does the rest of this guy look like? Well, we could take a look at the second derivative, okay, which I think we're going to be here for a while looking at. So let's look at the first derivative. Okay, let's look at the first derivative maybe around this guy. I know that my graph has got to go through this point. I know my graph has got to go through this point. I also know that the end behavior of my graph has got to be up in the two end directions. And the only way to do that, okay, the only way to get that to work is for my graph to go like this and then come back down like this. Now here, if it came up smoothly like that, then the derivative would exist, but it doesn't, so it must have a cusp at that point right there. Okay, so we've got a cusp here, we've got a maximum local, and then we've got a local minimum, it looks like, right here. And so the function takes on two local minimums, two global minimums, one local max, and no global maxes.